Alright, so this is my video. Alright, sorry. So this is my video explainer 5, and the scenario is asking if a sphere of mass m and radius big M and radius big R is rigidly attached to a thin rod of radius little r that passes through the sphere at distance 1/2 big R from the center, and a string wrapped around the rod pulls with tension T, find an expression for the sphere's angular acceleration, and the rod's moment of inertia is negligible, which, lovely, that's very helpful. So first, our strategy is really just going to be, we want to visualize it, we want to see a picture, know what all the forces and the torques are, and then I think this problem is somewhat clearly a torque problem, and it's asking for angular acceleration, and a relationship that we know or have learned is torque equals moment of inertia times the angular acceleration. And if we rearrange that, we get torque over moment of inertia equals angular acceleration. And so really we're just going to find the moment of inertia, which is kind of the trick of this problem, and find torque, divide them, and that's our expression, because we don't have real values, so we're just solving symbolically. And importantly, because this is really the whole heart of the problem, is the parallel axis theorem. The axis in this problem is not directly at the center of mass of the sphere, and so we have to do a little manipulating, sort of, to get the total moment of inertia of the sphere with the axis shifted 1/2 r. And so that is what this expression here is. That's the parallel axis theorem. It basically tells us find the moment of inertia if it was rotating about the center of mass. It's not in this problem, but find that. And then add on mass times the distance between the axis and the center of mass squared. All right, so that's what we're going to do. We know the distance, 1/2 r. And we know that the moment of inertia of a sphere, a solid sphere at least, and that's what this problem is asking about, although it doesn't state it, so I had to try twice actually, and that's kind of a tricky thing. But I guess you should just assume it's a solid sphere if they don't say it's hollow, because that makes sense, I guess. Is 2/5 mr squared. So we have that, and that's what we're working with. So there's our moment of inertia component. Torque is the next. We know that tension is really the net force. It's the only force acting other than gravity, but gravity won't produce any torque regardless in this case. So we just have to worry about tension, which makes our life pretty easy because torque is just force times radius. And because the tension is wrapped around that string, it's applying it at the radius of the string, which is a little confusing to say, but makes sense when you look at the expression where this has r, and this is the tension. It's wrapped around that. It's pulling at a distance r from the moment of inertia of the rod. Sorry. So torque in this case is just equal to tension times r. It's not at an angle, it's directly tangential, and so there is no need for the sine theta component, because that'll just equal 1. Sine of 0 equals 1. Or, sorry, no, sine of 90 equals 1. My mistake, yes, sine of 90 equals 1. All right, so let's solve for moment of inertia. So we get I equals 2/5 m big M r squared plus m 1/2 r squared. All right, that's kind of all there is to it. We just have to do a little solving here. So 2/5 m r squared plus 1/4 m r squared. And as you can see, this really makes things real straightforward for us. All we have to do now is, if we want to just add those fractions up and turn it into one expression, which I don't see why not, plus 1/4. And so then we use just a little algebra, and we get, let's see, 20 in the denominator. How nice. 4 times 5, 5, plus this times 4, 8. All right, so then we get our moment of inertia is 13, 13 over 20 mr squared. Boom. The last step, all we have to do, remember, torque equals I alpha, alpha being angular acceleration. And so then that equals torque over I equals alpha, which equals, in this case, just simply 13 over 20 mr squared with tr on top. If we simplify, we get 20 dr over 13 mr squared. And that is the answer. That's your angular acceleration. You really just, I mean, for this problem, it's really just important to remember that the axis is not at the center, and so you can't just use the 2/5 mr squared by itself. You have to add on the other thing. And algebraically, if you don't remember these parentheses right here and square the 1/2 as well as the r together to get 1/4, then your math's going to be a little bit off, and you'll have the right formula, just the wrong coefficients. And so when you're doing the algebra, you just have to keep that in mind. Thanks.